Grounding systems are essential for protecting satellite antennas from lightning strikes and electrical surges. The National Electrical Code, or NEC, Section 810.21. B states that satellite antennas must be grounded in accordance with Section 810.20 for antenna structures. NEC Section 810.20 specifies that antenna structures must be grounded using a grounding system that includes these components: firstly, a ground rod; secondly, number 10 AWG or larger copper grounding conductor; and thirdly, a grounding electrode system. For a 10-foot satellite dish, it is recommended to install a 10-foot copper-clad steel ground rod near the base of the satellite dish. Connect the ground rod to the satellite dish using number 10 AWG solid bare copper wire. Install a grounding bar near the receiver. Connect the coax cable shield to the grounding bar using a grounding clamp. Connect the grounding bar to the main service ground, typically a cold water pipe or grounding rod, using number 6 AWG solid bare copper wire. Consider these additional considerations. Use lightning surge protectors on all coax cables entering and leaving the receiver. Inspect the grounding system regularly and ensure all connections are tight and corrosion-free. Consider installing a dedicated antenna mast and grounding system to separate the satellite dish from the building's electrical system. The grounding system described previously meets the minimum requirements of the NEC. It is recommended to install a more robust grounding system in accordance with the above recommendations to provide maximum protection against lightning damage. The minimum grounding requirements involve using a number 10 AWG copper wire from the dish to ground rod, and then another number 10 AWG copper wire from the ground rod back to the main service ground. While this meets the basic code, it may not offer sufficient protection against a direct lightning strike. A more robust system involves several key improvements. Firstly, use a larger grounding conductor like a number 6 AWG copper wire for the connection between the grounding bar at the receiver and the main service ground. This provides a lower impedance path for fault current, improving protection. Secondly, install a dedicated ground rod specifically for the satellite dish system. This isolates the dish grounding from the building's electrical system, preventing potential ground loops and interference. The ground rod should be a 10-foot copper-clad steel rod driven into the earth near the base of the dish. Thirdly, use lightning surge protectors on all coax cables entering and leaving the receiver. These devices divert excess voltage to ground, protecting the receiver from damage. Fourthly, ensure all connections are tight and corrosion-free. Loose or corroded connections can significantly increase resistance, reducing the effectiveness of the grounding system. Regularly inspect the connections and clean or replace them as needed. Fifthly, consider installing a dedicated antenna mast to support the satellite dish. This mast should be grounded independently from the building's electrical system. The grounding conductor should be directly connected to the mast, providing a low impedance path to ground. The NEC provides specific guidelines for grounding and bonding electrical systems. Article 810 covers antenna systems, including satellite dishes. Section 810.15 addresses grounding of outer conductors of coaxial cables. It requires the outer conductor of a coaxial cable to be grounded as close as practicable to the point of entrance to the building. The grounding conductor should comply with Section 810.21, which specifies the size and material of the grounding conductor. Section 810.20 covers grounding of antenna structures. It requires antenna masts and structures to be grounded using a grounding electrode system that complies with Article 250. This typically involves connecting the grounding conductor to a ground rod, a metal underground water pipe, or other suitable grounding electrode. Article 250 provides detailed requirements for grounding and bonding electrical systems. Section 250.52 specifies the types of grounding electrodes that are permitted. Section 250.66 provides requirements for the size of the grounding electrode conductor. The size of the grounding electrode conductor depends on the size of the service entrance conductors. For most residential services, a number 6 AWG copper conductor is sufficient. The grounding electrode conductor must be connected to the grounding electrode using a listed connector or clamp. Grounding is a critical safety measure that protects people and property from electrical hazards. A properly grounded electrical system provides a low impedance path for fault current to flow back to the source. This causes the circuit breaker or fuse to trip, de-energizing the circuit and preventing electrical shock or fire. Grounding also helps to reduce electrical noise and interference, improving the performance of electronic equipment. In addition to grounding, bonding is another important safety measure. Bonding involves connecting all metal parts of an electrical system together to create a common electrical potential. This prevents voltage differences from developing between metal parts, which could create a shock hazard. Bonding conductors should be sized according to NEC Table 250.122. The bonding conductor must be connected to the metal parts using a listed connector or clamp. Surge protection is another important aspect of electrical safety. Surge protective devices, or SPDs, protect electronic equipment from voltage surges caused by lightning, power outages, or other disturbances. SPD divert excess voltage to ground, preventing it from damaging sensitive equipment. SPD should be installed at the service entrance and at branch circuits feeding sensitive equipment. SPD are rated by their surge current capacity, which is the amount of current they can safely divert to ground. The surge current capacity should be appropriate for the expected level of surge activity in the area. Electrical codes and standards provide detailed requirements for grounding, bonding, and surge protection. These codes and standards are developed by organizations such as the National Electrical Code, the Institute of Electrical and Electronics Engineers, or IEE, and Underwriters Laboratories, or UL. Compliance with these codes and standards is essential for ensuring the safety and reliability of electrical systems. Grounding systems are designed to provide a safe path for electrical current to flow in the event of a fault. This helps to protect people from electric shock and prevents damage to equipment. A properly designed grounding system includes several key components. Firstly, a grounding electrode. Secondly, a grounding electrode conductor. And thirdly, equipment grounding conductors. The grounding electrode is a conductive object that is buried in the earth and provides a connection to ground. Common types of grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes. The grounding electrode conductor connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Equipment grounding conductors provide a path for fault current to flow from electrical equipment back to the source. Equipment grounding conductors are typically made of copper or aluminum and are sized according to the rating of the circuit. Bonding is the process of connecting all metal parts of an electrical system together to create a common electrical potential. This helps to prevent voltage differences from developing between metal parts, which could create a shock hazard. Bonding conductors are typically made of copper or aluminum and are sized according to NEC Table 250.122. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, power outages, or other disturbances. SPD divert excess voltage to ground, preventing it from damaging sensitive equipment. SPD should be installed at the service entrance and at branch circuits feeding sensitive equipment. Electrical codes and standards provide detailed requirements for grounding, bonding, and surge protection. These codes and standards are developed by organizations such as the National Electrical Code, the Institute of Electrical and Electronics Engineers, and Underwriters Laboratories. Compliance with these codes and standards is essential for ensuring the safety and reliability of electrical systems. When dealing with grounding systems, it's important to understand several key concepts. Firstly, impedance is the total opposition to current flow in an alternating current, or AC, circuit. It's similar to resistance in a direct current, or DC, circuit, but also includes the effects of capacitance and inductance. A low impedance grounding system is desirable because it allows fault current to flow quickly and easily back to the source, tripping the circuit breaker or fuse and de-energizing the circuit. Secondly, ground loops occur when there are multiple ground paths between two pieces of equipment. This can create unwanted current flow and noise in the system. Ground loops can be avoided by using a single-point grounding system where all equipment is grounded to a common point. Thirdly, touch potential is the voltage difference between a grounded object and the earth. Step potential is the voltage difference between 2 points on the earth that are a meter or about 3 feet apart. These potentials can be hazardous if a person comes into contact with them during a fault. A properly designed grounding system will minimize touch and step potentials. Fourthly, transient voltage surge suppressors, or TVSS, are devices that protect electrical equipment from voltage surges. TVSS devices are similar to surge protective devices, or SPDs, but are typically used for low voltage applications. Fifthly, electrostatic discharge, or ESD, is the sudden flow of electricity between two electrically charged objects. ESD can damage sensitive electronic equipment. ESD can be prevented by using proper grounding and bonding techniques. Sixthly, electromagnetic interference, or EMI, is unwanted electrical noise that can interfere with the operation of electronic equipment. EMI can be reduced by using proper grounding and shielding techniques. Seventhly, harmonics are a distortion of the electrical waveform that can cause problems with electrical equipment. Harmonics can be reduced by using harmonic filters. Eighthly, power quality is a measure of the quality of electrical power. Poor power quality can cause problems with electrical equipment. Power quality can be improved by using power conditioning equipment. Ninthly, the National Electrical Code, or NEC, is a set of standards for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years and is used by most jurisdictions in the United States. Tenthly, the Institute of Electrical and Electronics Engineers, or IEE, is a professional organization for electrical engineers. The IEE develops standards for electrical and electronic equipment. 11thly, Underwriters Laboratories, or UL, is a testing and certification organization. UL tests electrical and electronic equipment to ensure that it meets safety standards. When installing a grounding system, it's important to follow these best practices. Firstly, use a qualified electrician to design and install the grounding system. Secondly, follow all applicable electrical codes and standards. Thirdly, use high-quality materials and components. Fourthly, ensure that all connections are tight and corrosion-free. Fifthly, inspect the grounding system regularly and maintain it as needed. Sixthly, keep detailed records of the grounding system. Seventhly, label all grounding conductors and equipment. Eighthly, provide training to personnel who will be working on the electrical system. Ninthly, use a ground fault circuit interrupter, or GFCI, to protect people from electric shock. Tenthly, use an arc fault circuit interrupter, or RSI, to protect against electrical fires. 11thly, use a surge protective device, or SPD, to protect electrical equipment from voltage surges. By following these best practices, you can ensure that your grounding system is safe and effective. A well-designed and maintained grounding system is essential for protecting people and property from electrical hazards. Remember to always consult with a qualified electrician for any electrical work.